Ever wondered how digital circuits or control systems work? They lean heavily on a concept called finite automata with output. This concept is a bit like an extension of the basic finite automata, only with the added ability to produce output while processing input symbols. Imagine a machine that not only moves from one state to another based on the symbols it reads, but also churns out a specific output based on the current state and the input symbol. A fascinating feature, right? Well, these automata are more than just a fascinating concept. They're a crucial part of the complex systems that power our digital world. From the circuits within your computer to the control systems that help fly airplanes, finite automata with output are at work. So buckle up, we're about to delve deeper into this fascinating concept. Output. To understand finite automata with output, we need to familiarize ourselves with some key components. The first component is the states, represented as Q. This is a finite set of conditions that the automaton can find itself in at any point in time. Think of it as the different moods of our automaton, if you will. Next, we have the alphabet, denoted as sigma. This isn't your typical ABCs, but instead, a finite set of input symbols that form the input string. Then we have the transition function, represented as delta. This function is like the brain of the automaton, dictating how it moves from one state to another. It takes the current state and the input symbol and tells the automaton where to go next. Now, here's where things get interesting. We introduce the output function, or lambda. This function associates an output symbol with each transition between states. It's like the voice of the automaton, expressing its reactions to the transitions it makes. We also have the initial state, marked as Qt. This is where the automaton starts its journey, the starting line of the race, so to speak. Finally, we have the accepting states, denoted as F. This is a subset of states from our set Q. If our automaton ends up in any of these states, after processing the input string, it gives a thumbs up and accepts the string as part of its language. Now, finite automata with output can be split into two main types, Moore machines and Mealy machines. In Moore machines, the output is tied to the state, independent of the input symbol. On the other hand, in Mealy machines, the output is tied to the transition and depends on both the state and the input symbol. These components make up the building blocks of finite automata with output, allowing us to create systems that can react dynamically to input, much like a chameleon adapts to its surroundings. With these components, we can create a system that reacts dynamically to input. Finite automata with output can be further categorized. First, we have Moore machines. Now let's dive into the fascinating world of Moore machines. Imagine a world where each state in your journey has a unique souvenir, a token of your travel, independent of the path you took to get there. That's what Moore machines are all about. They are a type of finite automaton with output, where the output is tied to the state, not to the transition or the input symbol that got you there. Moore machines are named after the American electrical engineer Edward F. Moore, who presented the concept in 1956. In a Moore machine, every state is paired with an output symbol. As the machine moves from one state to another, it produces the output associated with the new state it transitions into. So, let's say you're in state Q1 and you receive an input symbol that transitions you to state Q2. The output you'll get will be the one associated with state Q2, irrespective of the input symbol that caused the transition. It's like a destination-based reward system, where the reward is determined by where you land, not by how you got there. This makes Moore machines particularly useful in certain scenarios. For instance, when you need to design a system where the output is solely dependent on the current state of the system, a Moore machine can be your go-to model. It's a reliable system where the output doesn't fluctuate with the input. Instead, it remains consistent for each state. To sum it up, Moore machines are a type of finite automaton with output that ties output to states. They provide a consistent output for each state, regardless of the input symbol that triggers the transition. It's like a destination with a fixed souvenir, irrespective of the path you take to reach there. Moore machines are great when you need a consistent output for each state. Let's carry this understanding forward as we explore its counterpart, the Mealy machine, in the next segment. Next, we have Mealy Machines, another type of finite automata with output. Diving into the world of Mealy Machines, we find a slightly different approach to output generation. Unlike Moore machines, where output is tied to states, in Mealy Machines, the output is tethered to the transitions between states. This is a key distinction that makes Mealy Machines unique. Picture this: you're in a city, and each city block represents a state. In a Moore machine, the name of the block is the output. But in a Mealy machine, the output is the direction you take to move from one block to another. It's not about where you are, but where you're going and from where you're coming. The output in a Mealy machine is a result of a dynamic duo, the current state and the input symbol. It's like a dance, where the state and the input symbol move in sync to create the output. The output function, in this case, would be formally defined as lambda, q x sigma, lambda, where q is the set of states, sigma is the set of input symbols, and lambda is the set of output symbols. This characteristic of Mealy machines makes them particularly versatile. They can respond differently to the same input depending on the current state, providing a flexible and dynamic output generation capability. This is like being able to choose a different dance move every time a certain beat drops, depending on your mood or the overall rhythm of the song. But remember, just like in a dance, precision is key. The output in a Mealy machine is only as accurate as the state and input symbol it's based on. If the state or input symbol is incorrect, the output will be off-beat, leading to a less than perfect performance. In a nutshell, Mealy machines offer a unique take on output generation in finite automata. They tie the output to the transitions between states, making the output dependent on both the state and the input symbol. Mealy machines offer a more dynamic output, dependent on both the state and the input symbol. So, where do we see finite automata with output in action? You might be surprised to learn that they're integral to many areas of technology, playing a vital role in everything from digital circuit design to communication protocols. Let's start with digital circuit design. Finite automata with output are used to design sequential circuits, which are circuits where the output depends not only on the current input, but also on the sequence of past inputs. In these circuits, the automaton states represent the memory of the system, and the output function determines the output based on the current state and input. Next, we have control systems. These are systems used to manage, command, direct, or regulate the behavior of other devices or systems. In a control system, a finite automaton with output can model the dynamic behavior of the system, providing a formal framework for understanding and predicting the system's responses to different inputs. Communication protocols also heavily rely on finite automata with output. These protocols, which govern the exchange or transmission of data between devices, often involve complex sequences of actions that depend on the previous history of communication. Finite automata with output can model these sequences, providing a way to design and analyze the protocols. Lastly, we have pattern recognition. This is a branch of machine learning that focuses on the recognition of patterns and regularities in data. Finite automata with output can be used to model the patterns we're looking for, allowing us to design algorithms that can recognize these patterns in new data. These are just a few examples of how finite automata with output are used. They provide a powerful and flexible tool for modeling dynamic systems, and their applications are as diverse as the fields of technology that use them. As we can see, finite automata with output are vital in many areas of technology. Output. We've covered a lot of ground today, so let's quickly summarize. We've explored finite automata with output, a complex yet fascinating concept that brings together states, alphabets, transition and output functions to process input symbols and produce output. We've delved into its core components, from the finite set of states and input symbols to the transition function that guides the automaton from one state to another. We've also touched on the output function, which assigns an output symbol to each transition. We then differentiated between Moore and Mealy machines. Moore machines, where output is tied to states, and Mealy machines, where output is dependent on both the state and the input symbol. Finally, we've highlighted its applications in various fields, from digital circuit design to control systems, communication protocols, and pattern recognition. Finite automata with output, an essential concept for understanding how our digital world operates. Thank you for joining us today.